Anywho, I just want to touch on Kirchoff's rules before we move on. And this is probably the most difficult part of, actually not the rules themselves, but applying them to complex circuits. So a guy named Kirchoff came up with two rules that are related to conservation principles. The junction rule says that the current entering a junction, I already alluded to this, the current entering a junction must equal the current leaving a junction. So if you've got a circuit, and I'm not going to draw a full circuit diagram, but say you've got a circuit that branches off like this. Well, if there's current coming this way, this current has to be equal to the sum of the currents coming out of that junction point, that splitting point. What conservation of law is the basis of this? Well, this is conservation of charge, because charge has to go somewhere. If you didn't have the same amount of current leaving the junction that you had entering the junction, then you would have charge building up somewhere, which doesn't make sense because then it would repel itself and move along, or you'd have to have current or charge being created somewhere, which doesn't make sense. The other rule is the loop rule, which states that the voltage or potential difference around a closed loop, a closed loop meaning that you start and end at the same point, is zero. So if you've got a circuit, and you have whatever resistors, I don't know, whatever is going on, if you go all the way around the circle, then your voltage drop has to be zero, which makes sense, because if it wasn't zero, then this point would have a different voltage than this point, which doesn't make sense. If the potential difference was not zero around a closed loop, that would mean that going from here, coming back to here, you're either gaining or losing energy, and so that would violate conservation of energy. So the basis for the loop rule is conservation of energy. So the junction rule is based on conservation of charge. The loop rule is based on conservation of energy. So if we take a simple circuit, there's a lot of stuff going on here, but we can figure out the current in the circuit. So this is all in series. There are no branches, so we can just go around the loop. And what do we have going around the loop? Well, we know the voltage drop around the loop is zero. So if we start here, you can start anywhere, go in either direction, doesn't really matter. We pass through this battery. Okay, as we pass through that battery, the voltage increases by 12 volts. Then we pass across this resistor. Going across the resistor, well, actually we have two batteries, so we don't know off the top of our heads which direction current is going to flow, whether it's going to go this way or this way. You can probably guess this battery is bigger, so it's going to go this way. But let's assume we didn't know that. Let's say we assume that current is going to go this way. It doesn't matter. You make an assumption at the beginning, and if your answer comes out negative, that means current is flowing the opposite of the direction that you thought it was. So I will assume that current is flowing clockwise this way around our loop. So then we have a voltage drop across resistor 1. It's minus current times R1, which is 12. Then R2, we have another voltage drop, minus current times R2, minus current times R3. Then we go backwards through this battery, so that's another voltage drop, minus 15. And then we've got a voltage drop across this resistor, minus I times excuse me, R4, which is 22. From there, we can do the math. 12 minus 15 is negative 3. Move it over the other side. That's 3 divided by the sum, negative 12 minus 18 minus 38 minus 22. And that gets us the current of negative 0.03, which means our current is 0.033 amps, and it's actually going counterclockwise, which, depending on the problem, you may or may not be asked to state. That's the simplest level of application of Kirchoff's loop rule. Now, here's where things get more complicated, and we're just going to do one of these. There are one or two of them on your homework, but we'll spend all of next class doing examples of applying Kirchoff's rules to complex circuits. But here, we've got a pretty complicated circuit. It forks. There are two batteries, and that's just crazy. But we can figure it out. Now, in this, we have multiple unknowns. We don't know the current through any of the resistors. Okay, so those are unknowns that we have: I1, I2, I3. We have three unknowns, current through each of these three resistors. In order to figure those out, we need three equations, three unknowns. Now, we can always write multiple equations using Kirchoff's rules. We can apply the loop rule in multiple different ways. We can apply the junction rule. Now, just as a point of reference, there are three different loops that you could use in this circuit. You could go around this loop on the left side, you go around this loop on the right side, or you could go around the outer loop of the whole circuit. However, you can't do all three of those. You'll find if you do this loop and this loop, then this loop's equation will be redundant. It's an equivalent equation, because if you add the two equations together, you get the third equation. So to get a third equation, we do have to use the junction rule at least once. Okay. So where is our junction? Well, where does current split? We're going this way, up. There's a junction where our current splits. What do we have? Well, we assume, let's make assumptions about the directions of our current. Let's say I1 is this way, I2 is this way. This is the positive terminal of a battery. We'll say I3 is this way. Okay. I2 might actually be up, because this battery is bigger than that one, but whatever. So if I3 is this way, and I3 is in series with this battery, so I3 is the same as the current over here. So we've got, going into the junction, we have I1. Coming out of the junction, we have I2 and I3. So based on the junction rule, we have I1 equals I2 plus I3. Junction. That's from our junction rule. Okay? Then we can start writing loop rules. Loop 1, I'll take this loop around over here. Call that loop 1. What happens? Starting here, we go through a battery. So our voltage increases by 5. Pass through a resistor, voltage drop. I1, R1, which is 15. Pass through this resistor, voltage drop in the direction of current. I2 times 28. And there's nothing else over here. That's one loop. And we can use this loop. Call this loop 2. Voltage drop is 0. This resistor we go through, but we go through it in the direction opposite of where we've assumed our current to be. So that would be a voltage increase. So we've got a positive I2, R2. And we go through a battery. That's a voltage boost, going the right way through a battery. So we got adding 9 volts, and we've got a voltage drop across our third resistor. So now we've got a system of 3 equations, which we can rearrange. So you may or may not remember, but you can use matrices to solve systems of equations, and we'll do this just using our calculators. So you want to get all your unknowns, all your currents on one side of your equation, and your variables or your numbers on the other. So this one, we've got I1 minus I2 minus I3 equals 0. Over here, I'll move this 5. Well, actually, I'll make everything positive. So we've got 15 I1 plus 28 I2, nothing I3, equals 5 I move these two terms to the other side. And here, we're going to have to subtract, but I'll move the 9 over, so that's a negative 9 equals, what do we have? And just for the sake of lining it up, I'll move it over. We got 28 I2 minus 8.5 I3. Okay. Now you may or may not remember, but this system can be represented by a matrix. So with the entries of the matrix being the coefficients and then the numbers over here. So the coefficients in my first equation are 1, negative 1, negative 1, and that's equal to 0. Here are my coefficients. We've got 15, 28. There's no I3, so the coefficient there is 0. That equals 5. 0, 28, negative 8.5, negative 9. So how do you deal with this? Well, I'll show you on the 83 and the 84 is the same. If you've got an 89, I'll have to show you separately. I can show you, or you can figure it out yourself. But they all can do matrices. So I go second, and then matrix is right on this x to the negative first button. That's where the matrices are. And we want to create a new matrix, so we go to edit, pick any old matrix, doesn't matter. And we want a 3 rows, 4 columns. Type in our numbers, 1, negative 1, negative 1, 0, 15, 28, 0, 5, 0, 28, negative 8.5, negative 9. Okay, I've typed in my matrix. And then go second matrix and math. And this is something that will solve the matrix for you. RREF. That stands for reduced row echelon form. If you don't remember what that means, go back to your pre-calc notes. Or actually, you're probably doing that right about now in pre-calc, if you're in pre-calc right now. RREF, go to matrix. That was matrix A. And what this does, ultimately, and you'll learn why in pre-calc, is it solves the matrix. So this, over here, you have the identity matrix, and then these are your 3 solutions over here in order. So from this, we see that our current 1 is equal to 0.55 amps. Current 2, it's a negative, which means it's in the opposite of the direction I assumed. So it's actually going upward through the resistor instead of down. But it's negative 0.12 amps. I3 is equal to 0.67 amps. So anytime we have a complex circuit, we'll generate a matrix, 3 linear equations, and solve them using the calculator. So enter the matrix, and you type RREF. Stands for reduced row echelon form. And I can show you that in person if that's confusing. Just ask and help. I'm sure that your Mr. Torone, at least, could also help you with that. Got your homework? See you next time.